In our last video, we discussed a p-n junction under forward bias. That is, when a positive voltage is applied to the p-type region with respect to the n-type region. As the external voltage and the corresponding electrostatic potential drop across the depletion region is opposite to the built-in voltage of a p-n junction, the built-in voltage is decreased and the depletion region becomes narrower. A net current flows through the p-n junction diode. In this video, we will see what happens when we apply a reverse bias to a p-n junction. Here we see a schematic picture of the electrical connection of a p-n junction at reverse bias voltage condition. As you can see, this time we apply a negative voltage to the p-type region with respect to the n-type region. Let's take a look at how this affects the p-n junction by first using the bonding diagram. Again, we start with a p-n junction at thermal equilibrium. Remember that there is a depletion region at the p-n junction interface. The diffusion of charge carriers is counteracted by the drift caused by the internal electric field in the depletion region. When these two currents are balanced, the width of the depletion region can be defined. If you remember from the previous video, a forward bias shrinks the depletion region and allows majority carriers to diffuse across the depletion region into quasi-neutral regions, where they become minority carriers and recombine. This turns the p-n junction diode into a conducting device. So let's apply the reverse bias voltage and see what happens. As we mentioned in the previous video, when we apply voltage to a device, the potential difference corresponding to the applied voltage is spread across the depletion region. Under reverse biased conditions, the applied voltage will spread across the depletion region such that the potential at the edge of the depletion region in the p-type material is negative with respect to the n-type material. The built-in voltage of the p-n junction has the same potential difference, therefore the built-in voltage and the reverse applied voltage add up. The electrostatic potential difference across the depletion region has increased. This potential difference across the depletion region is often called a potential barrier that prevents diffusion of majority carriers across the junction. The depletion region gets broader, and the internal electric field expands into a larger part of the p-n junction. It is the drift current that depends on the magnitude of the internal electric field. Therefore, we expect the drift current to increase. Since the internal electric field is negative in the depletion region, it pushes electrons from the p-type material into the n-type material. We have to remember that electrons in the p-type semiconductor are the minority carriers, and their concentration is very, very low. When extending the internal electric field deeper into the p and n-type regions, we start drifting minority carriers from these regions across the depletion region. You see an animation where a minority charge carrier, in this case electron in the p-type region, makes it to the depletion region, and the electric field will push it towards the n-type region. The small number of minority carriers that are pushed by the internal electric field are replenished by the external voltage source. The external source injects minority carriers into the p and n-type regions. Here we can see an electron injected into the p-type region. Since the concentration of minority carriers is very small, also the net drift current is extremely small compared to the net current in case of forward bias voltage that is driven by majority carriers. Please note that positive charge carriers leave the p-n junction diode into the external circuit from the p-type region. This means that when we apply the reverse bias voltage, the electrode that is attached to the p-type region becomes cathode. Now that we understand the concepts in the bonding diagram, let's take a look at the band diagram. In this slide, we see the band diagram and electrostatic potential of a p-n junction diode at thermal equilibrium. We see only one Fermi level across the whole p-n junction, and the built-in voltage across the depletion region is such that the potential at the p-type region is negative with respect to the n-type region. In the simulated p-n junction diode, the built-in voltage is 0.9 volts. Let's apply a reverse bias of 0.1 volts. When the p-n junction is reversed biased, a negative voltage is applied to the p-type region with respect to the n-type region. The overall potential difference across the depletion region is increased, as you can see in the diagram on the right side of the slide. The quasi-Fermi levels split, but this time in opposite direction than in case of the forward bias condition. This indicates that in the region where the quasi-Fermi levels are split, the concentration of charge carriers is less than their concentration at thermal equilibrium. If you remember from the previous video, the curve in quasi-Fermi levels indicates that current is flowing through a device. So the slope in the quasi-Fermi levels clearly shows that there is a current flowing through the device, and the direction of the slope indicates that the net current flows from the n-type region to the p-type region. To summarize this video, we looked at what happens to a p-n junction when a reverse bias voltage is applied. While forward biasing turns the junction into an extremely good conductor by shrinking the depletion region, reverse biasing has the opposite effect. In this case, the depletion region widens, the internal electric field is enhanced, and is responsible for the drift of minority carriers that is not compensated by the diffusion. This extremely small drift current across the depletion region is facilitated by the injection of a small number of carriers from the external source, causing the small current in the external circuit. This current has, however, the opposite direction as the current that flows through the circuit at forward bias voltage. Furthermore, we looked at the band diagram as well. Here we observe the quasi-Fermi level splitting that is opposite to that of forward biasing. Now that we have understood what happens when we apply a forward or a reverse bias to a p-n junction, we can derive the current voltage characteristic of a diode. This characteristic is extremely important to know and understand for a photovoltaic engineer. So I look forward to showing it to you in the next video.